Okay, this is the third video in chapter 10. I had just done in the previous video I showed carbonate and I showed the resonance forms of the carbonate anion in the Lewis notation. I want to make a couple comments about this. So it's a common mistake, I guess, or a common habit for some people to make, to think that the three resonance forms that I showed in the previous video of carbonate, it's easy to think that, oh, I see, the electron pair just moves. So some of the time it's actually here, some of the time it's here, and some of the time it's here. And so you can think of it, or it's easy to make the mistake of thinking that these three resonance forms actually that the electrons actually move so that some of the time it looks like this, and some of the time it looks like the other two forms. That's actually not the case. And if you think back at chapter 7 and 8, when we were talking about the electrons, this mistake is because we think that electrons are always somewhere, like somewhere specifically. But if you remember, electrons they have this kind of spooky nature of really resisting the notion that it's in one specific place. And this resonance form, what's actually happening here is that the electrons have this wave pattern, and so that they're actually in these three states that I drew simultaneously. And so in fact, when you look at each of the bonds here, each of the bonds are kind of like 1 1/3 bonds each, in terms of how the physical properties are and even the shapes, and we'll get into that again once we start getting into shapes. So I just want to kind of mention that this concept that the resonance forms are not, it's not like the molecule changes from one form to another and back and forth, even though it's kind of, sometimes it's comfortable to think of it that way. But in reality, they actually coexist in these forms simultaneously. And again, that coexistence actually, it's called delocalization of electrons, or another term for it, actually lowers the total energy of, meaning makes more stable the molecule. Okay. The classic example of this idea of the coexistence of the resonance forms comes about in benzene. I'm going to draw it real quick. I'm not going to go through the rigor of doing the counting valence electrons and all that. You could do that as a kind of as a sample problem after you watch this video. But benzene is interesting in that it is a ring of 6 carbon atoms. And again, and it also at the attached to each carbon is a hydrogen. Okay. Now you're probably maybe already comfortable with the fact that carbon, so far in every example we've used, carbon always ends up having 4 bonds to it, 4 lines. We've never had a situation where carbons ended up with a lone pair, and that's very common. You'll see, especially when you get into organic, that's very, very common. So in this case, clearly we need to have a double bond, a set of double bonds. So one way of doing this is to have a double bond here, here, and here. And if you look at this carefully, you'll see that every carbon atom actually now has an octet around it. Okay, and of course each hydrogen has 2, which is correct also. But that's not the only way we could have done this. So in this case, I did it at essentially at 11 o'clock, 7 o'clock, and 3 o'clock. Thinking about this as a clock. We could have easily done it in a different way, though. We could have done it at this one, and this one. Essentially at 1 o'clock, 5 o'clock, and 9 o'clock. Just thinking about this. So it's easy it's easy but not correct to think about benzene as actually kind of transferring between the 2 forms, this form and the other form. In reality, it doesn't do that. And in fact, what happens is that each of the carbon-to-carbon bonds is almost, it kind of behaves like about 1 1/2 bonds each in reality. And so it's kind of a superposition of the 2 resonance forms that I drew. And in fact, a lot of times benzene, because of that nature, is actually depicted with a circle in the middle. So a lot of times you'll see this when you look at chemical formulas, especially in organic chemicals. Whenever you see a ring of carbons, or even sometimes a ring that doesn't even have the carbons shown. Like, let's see if I can possibly draw it. Nice little hexagon. That's a symbol for the benzene. It's called the benzene ring. And again, the circle is just kind of a reminder of the fact that this has two very common resonance forms, and the superposition of them makes it so that it's like this this ring is made up of 1.5 bonds each between the carbons. Okay, so that's all I want to say about resonance for now. For now, anyway. But we'll continue to talk about resonance forms, because you'll see in some of the Lewis structure problems, when you do a check, it doesn't come out that everybody has an octet right away, and there's a lot more work. Okay, now I'll throw one example in right away. That is kind of an introduction to the next concept. How we doing with time? All right, the next sample molecule I want us to work on is carbon monoxide. Remember, we did carbon dioxide, and that turned out to be pretty easy. Carbon monoxide is a little bit different. So let's do what we always do. We'll start with the least electronegative atom, which is carbon. And then we'll bond that to all the rest of the atoms. In this case, there's only one, oxygen. And let's actually count up our valence electrons. The carbon has 4, and the oxygen has 6, a total of 10. It's neutral. It's not an ion, so 10 is the correct number of total electrons. Okay. Well, I've drawn in 2 of them. Now you can see carbon's going to need a bunch here. So let's put in one more pair for carbon, another pair for carbon. Well, we're running out, aren't we? Now let's see. Let's put in the other pair. That's 2, 4, 6, 8. We only have 2 more. Let's put them there. Okay. So that'll be our first attempt at this, using up all of our 10 valence electrons. All right, let's look at now and see how we're doing with the octet rule. Well, carbon has 8, 2, 4, 6, 8. Now, the oxygen only has 2, 4. It's short. It's short by 4 electrons. All right, remember the technique we used. We'll take one of these pairs and move it up here. Now let's look at it again. Carbon's still fine. Oxygen's closer. It's got 6, but it's still missing 2. Okay, so let's take the next 2, put it here, make a triple bond. And remember, the last couple examples I was talking about double bonds, but triple bonds are also possible, and they're especially possible when you involve carbon and nitrogen. Again, you'll see this in organic quite a bit. So now when we do this, it looks like we finally arrived at a situation where both the carbon and the oxygen have an octet. And this indeed is the Lewis structure for carbon monoxide. There's kind of an issue with this, though, that is different than the other molecules that we've encountered so far. Okay. Now I want to compare this and introduce a new concept. Let's see if I can do that. Yeah, I think I can. Nope, I bet I can't. So I'm going to stop this one, and I'm going to pick up on the next video. Is going to talk about something called formal charge, and I'm going to start with carbon monoxide, compare it with some of the other molecules that we've done Lewis structures for already.